Okay, so this is the process of glycolysis. Glycolysis means sugar splitting in Latin, and that's basically what the process does. It takes 6-carbon sugar, glucose, and breaks it down into 3 carbon sugars. So we're going to begin then. So you start with your glucose, which is your 6-carbon sugar, and that will meet hexokinase, which is the enzyme. And hexokinase will take an ADP and strip it of its phosphate, one of its phosphate groups, so you'll end up with ADP. Now, the phosphate group is important in keeping the glucose in the cell because due to the charge on the phosphate, it will not let the cell go outside. It will not let the glucose go outside the cell because the plasma membrane on the cell is impermeable to large ions. So the phosphate group is basically holding the sugar inside the cell, holding it hostage, if you could say. And that'll create glucose 6-phosphate. Now, that'll meet phosphoglucoisomerase. So it's just going to make glucose 6-phosphate isomer, fructose 6-phosphate. Now, fructose 6-phosphate will meet phosphofructokinase, and phosphofructokinase is a really important allosteric regulator. It is inhibited by ATP and stimulated by AMP. So, if you have a large production of ATP, phosphofructokinase is going to stop working allosterically. The ATP is going to bind with one of the sites on the phosphofructokinase and prevent it from bonding with any more of its necessary substrates. That's the word I was looking for. So that's going to halt the glucose cycle basically, and any other place that phosphofructokinase is used is going to stop that process because the cell is creating feedback and saying we've got plenty of energy, you can stop. But if there's AMP around, that means that phosphofructokinase needs to continue what it's doing, and so that will stimulate the enzyme and it will begin production again. So phosphofructokinase will take in an ATP, strip it of its phosphate group, and it'll bind with the fructose 6-phosphate to create fructose 1,6-bisphosphate. And this is where we get into the real sugar splitting part of glycolysis. Fructose 1,6-bisphosphate will meet aldolase, which will then divide it into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. And these are kept in balance by isomerase. Now, glyceraldehyde 3-phosphate is what's going to be used to continue glycolysis, and dihydroxyacetone phosphate, it doesn't need to be involved in glycolysis. It's not important besides that it's the product of fructose 1,6-bisphosphate dividing. But isomerase makes sure that there is enough production of both of them, and glyceraldehyde 3-phosphate is taken as fast as it's made. But because the only one that's needed in the process is the glyceraldehyde 3-phosphate, there's never an equilibrium, which is good because it means that you're not going to die, basically. So glyceraldehyde 3-phosphate meets up with triose phosphate dehydrogenase, which will accept 2 NAD pluses and donate 2 electrons and 2 H pluses. And so you get the release of 2 NADHs and 2 H pluses. Additionally, 2 phosphate groups will join up with the party, and the inorganic phosphates, they just kind of lie around in the cytosol. They're there all the time, and when they're needed, they're just like, okay, let's go. So they'll join up, and it'll create a lot of energy, this part of the process, because you're getting those NADHs and the hydrogen ions, and you're taking in those phosphate groups. So your potential energy is very high. Up until now, you've just been investing energy. You've taken in those 2 ATPs, so you're using energy. So now you're trying to pay that off with exergonic processes. You're trying to roll the ball downhill and get more energy, since you've been pushing it up the hill for the past few steps. So you get your release of energy there, and you take in the 2 phosphates, and you get 2 1,3-bis phosphoglycerates. Now from here on out, there will be 2 of everything, but for the sake of simplicity, I'm just going to show one part, but know that each process happens twice. So you take one of your 1,3-bis phosphoglycerates, and it meets up with phosphoglycerokinase. And that will take in an ADP and donate one of the inorganic phosphates to create ATP. And that will create 3-phosphoglycerate. So basically, you don't have sugar anymore. You just have another molecule, because you've lost the carbonyl group, and now you just got that carboxyl group on there. So the 3-phosphoglycerate will meet up with phosphoglyceromutase, which will just move one of the phosphate groups that's attached to the molecule to create 2-phosphoglycerate. And that will meet up with enolase, which will remove the water. And anytime you see enolase, that normally means removal of water. So you get that one water gone to create phosphoenolpyruvate. And that will meet up with pyruvate kinase. You'll get an ADP, and that last phosphate group that's attached to the molecule will be donated to create ATP, and you get your pyruvate, which is what you've been waiting for. So you started off with taking in 2 ATPs, and like I said, the processes I went over happened twice, so you've got a gross gain of 4 ATPs. So your net gain is 2 ATPs, plus you released the 2 NADHs and the 2 H pluses, which can be donated into other processes to create more ATP. So basically, you took in 2 ATP to just get a bucket load of energy, and that's glycolysis. And the next step is what I refer to as the junction, which is the steps between glycolysis and the citric acid cycle. And I will go over that in the next video, but right now you got your pyruvate, and you're ready to go with the rest of the cellular respiration process.